Hello grade 9 integrated science. I'm making a video to go over your first test. Your job is to watch the video, it's quite long, pause it, check your answers, make sure you understand. Okay? It's going to be about a 10-minute long video, so you probably want to let it stream and download and then play it after. Okay? Hello freshmen, I've just realised I've got face paint all over my computer. Not to worry. Anyway, we're going to go over your first science quiz. And if you look at the screen, I'll go through the questions one by one. So, for example, we'll start with question number 1. Significant figures. I've already highlighted the significant numbers here. So I'm going to talk through why I've highlighted what I've highlighted, and then we'll work out how many significant figures there are. So, 1a. Alright, we can rewrite this number as scientific notation. These two zeros are trailing zeros. They don't count. They don't mean anything, which means this, the only number that matters is the number 5. There's only one significant figure. There is a 0 in here, but it's sandwiched between other numbers, which means these are all significant. So we have 1, 2, 3, 4, 5 significant figures. Alright, we do have a trailing 0 here, but it's after the decimal point, which means we actually measured it. We actually measured 0, so it's significant, which means there are 4 significant figures. Alright, over here we have the number 6, so we have an actual number with a 0 after it. So this is significant because there's a decimal point, so after the decimal point, the zeros after the numbers, this matters. We measured this, but these two zeros are placeholding zeros. We can get rid of them. We could rewrite this number as scientific notation and lose them. So there's only 2 numbers that matter. Here, again, we have 2 numbers and trailing zeros, same as the first one, so there are only 2 that matter. Here, we can rewrite this whole number without these zeros, using scientific notation. So there's only 1 number that matters. Okay, so that's question number 1 done. Let's follow the same process for the rest of them. Okay, so 670.29, the whole number needs to appear. 670.29. I'm going to move my decimal point 2 places, 1, 2, to here, which means I do times 10 to the 2. Okay, 4310. All the numbers are significant, all need to appear. How many times am I moving my decimal point? 1, 2, times 10 to the 2. Over here, alright, the only numbers that need to appear are the 6 and the 0. What am I doing to my decimal point? 1, 2, I'm moving it negative 2, I'm going the other way. Times 10 to the minus 2. Again, only numbers that need to appear are these ones, so 37. What am I doing with my decimal point? I'm going 1, 2 that way, so that's times 10 to the 2. Alright, only number that needs to appear is the 9. What am I doing to my decimal point? 1, 2, 3. So times 10, you got it by now, to the minus 3. Hooray! 6 out of 6. Alright, volume of a tomato, not a very regular shape. You cannot measure that with a ruler. It's impossible. It's not even circular. Alright, so you're going to have to use displacement. You have to displace some water. Okay, so you're going to need a displacement can, or sometimes they're called Eureka cans. How do you spell that? A Eureka can. And a measuring, God, my handwriting's dreadful. Cylinder. So a measuring cylinder or a Eureka can. What would the unit be? You know, it would be cm cubed, because that's what volume is measured in. Alright, volume of milk. Well, that's a liquid, so we can just use a that look like cylinder? Nearly. Units, well, we could just go straight in with millilitres, or again, centimetres cubed. Alright, time. What do you think you're going to measure time with? You're going to measure with a stop, watch. Right, unit, seconds. Not minutes, that's nonsense, not hours, it's seconds is the SI unit. That's what we should be measuring it with. Mass of a 10 peso coin, really, it's pretty small mass, so I would say the digital. What the fuck? Mass of a 10 peso coin. So I would say, well, it's got a small mass. So a digital scale units. What's the SI unit for mass? It's actually bizarrely, it's the kilogram. However, this is a pretty small thing, so grams is fine as well. Alright, thickness of a credit card. Well, it's less than a millimetre or around a millimetre, so a millimetre ruler is not really going to measure precisely enough. So we want to use something called a vernier caliper. Okay, don't let me down. A vernier caliper. Okay, what would the unit for a vernier caliper be? Well, I mean the SI unit for any distance is metres, so you could put that, but actually you could put cm or because they're a bit more sensible for something this small. Okay, question number 4. Figure 1.1 shows how a student used a ruler to measure h, the height of a pile of wooden blocks. Jolly good. The reading was inaccurate because the student's practical technique was poor. Okay, the student's a donut, right? Why is the I away up here if you're trying to read something that's down here? That's bad. Okay, why is the 0 lined halfway up the blocks? That is also bad. This needs to be fixed. Complete figure 1-2 to show the correct method to read the height h using the 30cm rulers. Well, you probably want to get your ruler and actually start. Whoa, that's not a very good drawing of a ruler. Your 0 cm aligned with the bottom of the block that you're measuring. And if you want to take a reading, this is an eye, by the way. It's not a very good drawing of an eye. Okay, you want to make sure that your eye is level with the thing that you're reading so that you don't get a systematic error. Okay, either of these two reasonable suggestions will get you 1 mark. Use your ruler to measure the height, h. Okay, if you'd actually measured the height of all of these blocks, you should have found it to be 14 millimeters or 1.4 cm, something like that. 1 mark. A pretty easy 1 mark measuring something with a ruler. Okay, it's drawn to scale. Part C. It's a fifth of the actual size. Calculate the actual thickness of 1 block of wood. So we've said that, how many blocks are there? 1, 2, 3, 4, 5. There are 6 blocks of wood. Alright? They are cm high. There are 6 of them. So 1 is 0. And I have no idea what it is, 0.23333, something like that. So yeah. Okay, so that's what 1 block is. But it's done to scale. So the actual drawing is a fifth of the size. So what is the actual size of 1 block? We'll do 5 times 0.23333. This is going to give us a number, something like this, 1.1665 cm. Again, that's all well and good, but there's far too many significant figures. We're going to have to tidy that number up a little bit. There's too many significant digits in that. There are only how many significant digits? Here, there are restart again. Alright, olive oil was poured into three 250 cm cube measuring cylinders. Three, alright. First two cylinders are filled to the 250 cm cube mark. Okay. Third has a little bit more, it's not to 250. So where does the third one go? Goes to here. So how much is that? Okay. Well, if this is 50, this is divisions of 1, 2, 3, 4. Okay, this must be 40, 30, 20, 10, and that would be 0. So if it's halfway between, roughly, I can't tell anymore, I can't be more precise than that. It's approximately halfway between 10 and 20. So halfway between 10 and 20 is 15 cm cubed. Alright, calculate the volume of the olive oil in the unopened bottle. So what's the total volume? So I've got, let's go, total volume, well we had two 250s and they were full. So that's going to be 250. There's two of them, 250. And then that little bit left over, which I've just worked out, is 15. So my total volume is 515 cm cubed. I'm getting bored now. Right, 515. Excellent. So I've got the total volume. I've got the mass, which means I can work out something called the density. So density equals mass divided by volume. What was my mass again? Density equals, right, what was my mass? Okay, 0.47 kilograms. So I'm going to put in, substitute in 0.47 kg. Right, what was my volume? 515. 515 cm cubed. So what is my density? Right, so if I divide 0.47 by 515, I'm going to get a pretty horrible number. 0.0091262. Don't like that. Too many numbers. Alright. How many significant figures should I have? Well, really, this has got 2, this has got 3, but actually, as it's a division, we should look at sig fig. So actually, really, that's got 2. Our final answer should really only have 2. Right? We're not going to go mad on this. So really, the final answer should be 0.00091. That will be the final answer. What's our unit? Kg per cm cubed. Hooray! Okay, nearly there, boys and girls. We're on to question number 6. Question number 6. Alright. In an experiment to determine the volume of glass beads, a student used a displacement method to determine the volume of a glass bead as shown in the diagrams below. Right, so what's going on here? So we've got a certain amount of liquid. What's that? It's about 80, right, cm cubed. We drop in 245 glass beads. Oh, and the liquid goes up. What's it going to go up to? Yeah, it's sort of hard to tell. I reckon it's about 95, 96. I'm not quite sure. So I say 95 cm cubed. Or is it 96? Is it above? Yeah, it's hard to tell, to be perfectly honest. So we'll say 95. Okay. So you're asked to write down the values of the readings taken, so it should be 80 cm cubed and 85 cm cubed. I reckon we get away with 96 cm cubed, because it could be a little bit more. Right, calculate the volume of the 245 glass beads. Right, well that's going to be the total volume that we had again, displacement, so that'll be 90, let's just take 96 cm cubed minus, before we put the glass beads in, which was 80, so what do we end up with? 16 cm cubed. So there's our volume. Calculate the average volume of one glass bead. How are we going to do that? Okay, so we displaced 16 cm cubed. How many glass beads did we put in? 245. So to get the volume of 1, divide by 245. And our answer is going to be 0.065 cm cubed. There may be a whole load of other numbers, which we're going to round it up to 2 sig figs, right? Like 1, 2. Because this has, oh, easy tiger. Because this has 2, right? 2 sig figs. Our answer will have 2 sig figs. 0.065. Or you could even round up a little bit more. Done. Stop. Alright, question number 7. Person winds some thread tightly 3 times round the length of a meter ruler and cuts the end off level with the left hand end of the ruler. Okay, so that's here. As shown in the diagram below. So it's going to wrap round 3 times. So if I wrapped round once, it's a meter ruler, that would be along, that's 1 meter, and then round and back. Whew, so that's 2 meters. But I'm going to do that 3 times, so that's once round. Okay. And then I'm going to go around again. 2, 3. So we'll do that 3 times. So 3 times 2 equals 6. So to the nearest meter, alright, so it's probably going to be a little bit more than that, but to the nearest meter it's 6 meters. Right. Is the actual length of the thread slightly greater or slightly less? Right, well, it's greater. Why is it greater? Let's look back. As we wind it round, so along, and then go right around the edge a little bit, so it's a meter, and then a little bit more, and then back, and a little bit more, and then round. So there'll be like an extra bit. So reason is when we wrap it around corners, have extra, what we call it, thread. So it's going to actually be a little bit longer, okay? That's for 2 marks. 1 mark for saying it's greater, and 1 mark for saying why. Alright, last question. An integrated science class, oh, it's you. An integrated science class was asked to investigate the factors affecting the time, okay, it takes water to boil. Right. Okay. One student decided to investigate the effect of changing the volume of water. Right. Okay. Excellent. So we've got 2 variables identified here. Let's just highlight what they are. Okay, so one is time, right? And then the student decides to change the volume. Okay, so which way round are they? So we'll have question. What is the dependent variable? The dependent variable. Alright, so which one are we measuring? Well, we're measuring the time it takes to boil. Should really put the unit in. Right, some of you wrote how long it takes to boil. Because I'm incredibly generous, I think I'll take that because it does say, but what you shouldn't be saying how long. What is the variable? What is the variable? The variable is time. So it should be time in seconds. Okay, what's the independent? So what was this lad changing again? Oh, it was changing volume. Probably in cm cubed. Alright, 1 mark for each. List 3 possible variables that should keep constant. So what other things could be affected? Well, probably the initial temperature of the water. Initial temp of water. Because if the water was hotter, start with it wouldn't take as long to boil. Right, I mean, it's not really a variable, but I suppose you should control maybe the apparatus. I don't even think here. Same apparatus, so for example, the same type of beaker. And then finally, what else could we have? Well, I suppose different Bunsen burners, blue flame, yellow flame. So Bunsen burner temperature. Actually, and anything else. My handwriting's atrocious. Anything sensible. Any 3 sensible things will get you marks here. Right, you don't start talking about how you're going to measure the time. You don't start talking about how you're going to change the volume. That's not the control variable, that's how you're changing, that's your dependent, and how you're measuring. Okay, it's all the other things that you need to keep constant to make it a fair test. Okay, boys and girls, sorry about my handwriting. I'm looking at this and it is disgraceful. Okay, I'm not very good at writing, but I'm good at graphs. See you later. Bye.